Hello everyone. The most important system that we use for the launch vehicle is a propulsion system, and some of the propulsion system also used in satellite, but we're going to see generally what we have in propulsion system. You're going to go deeper on this topic in the propulsion class, but here just an overview for you to have a knowledge on this propulsion system. So what we're going to cover for this, we're going to describe the key element of the propulsion system and a few basic principles for the different types of propulsions, and also we're going to discuss on propulsion that produce thrust without mass, and lastly a few equations that we can use to calculate on this propulsion system. Okay, let's have a look on this propellant management. So to design a specific system, we need to start with the desired thrust, or usually in some very specific time. So we have a thrust and we want to use this thrust in specific time. So this is going to be the input for this propellant management system, and the propulsion system controller manage these inputs and formulates the command to send to the propellant management system, which is it sent to the actuator, the propellant management actuator, which it can turn the flow of the propellant on or off. So first, you can see that this propellant management system is including also on the controller. Controller meaning that from the electronics system, you need certain value to be given to this management system, but this is being calculated on how much the thrust that it desired. Then for some system, the controller also manage the energy input to the rocket. For example, here in the electrodynamic rocket, the system has no interface with the spacecraft electrical power system to ensure it provides the required power. And the controller uses sensors extensively to monitor the temperature, the pressure of the propellant through the propellant system. So from this propellant management system, and it's going to feed back to the rocket by giving the thrust. So this is the idea how the propulsion actually being controlled or be managed so that we can get the desired thrust. So this is two classes of thermodynamic. Two rocket classes, which is one is thermodynamic, another one is electrodynamic. So on the thermodynamic, we have cold gas, chemical, solar thermal, thermoelectrics, and nuclear thermal. While electrodynamic, we have ion thruster and plasma thruster. For this thermodynamic, on the chemical side, we have solid, liquid, and also hybrid. And nowadays, actually, most of the rocketeers using hybrids. And in liquid, we have biopropellant, we have monopropellant. So this is a few types of rocket class that we can use for the rocket, and it depends on actually how the thrust is produced. And but for this class, we will cover on this a few things on the thermodynamics and electrodynamics. Okay, on the cold gas propulsion, if you see here, this is the example of cold gas propulsions, and the propellant that used for the cold gas is is nitrogen, helium, nitrous oxide, and butane. And if you see here how it's work, it releases a gas through the nozzle. So we have this propellant tank that consists of gas, and it's released through the high pressure valve here, and when it's released, it's going to generate a thrust. So this is very simple concept of thruster. So this is how it's used. Okay, then we have this chemical propulsion system. So we have liquid, solid, and hybrid. So for the liquid, we have two types: monopropellant, bipropellant. Monopropellant meaning that we have only one propellant used. Bipropellant is a mix of two liquid propellants. We call that fuel and oxidizer. So normally fuel we use liquid hydrogen, oxidizer we use liquid oxygen. And for solid, the fuel and oxygen normally is bind together, it's solid. And for the amateur, normally we use solid, amateur rocket. And also for the space shuttle, they use this solid propellant. And for the hybrid, it's actually combination between the solid fuel and also the liquid hydrogen, and always used for the sounding rocket too. Okay, this is the example of a rocket using, if you see here, there is separation between fuel and oxidizer. So this will be the bipropellant. So if you see here from the combustions, the more fuel grain from the combustion chamber and oxidizer is injected to this combustion chamber. So this is the combustion chamber, and initiate the thrust for the rocket. For the monopropellant system, we normally use liquid propellant, and we have hydrogen here, we have nitrogen or helium inside this propellant tank, and we have the same system. We have valve, isolation valve, and from here we use this fuel to in the high pressure to give a thrust for this system. For the bipropellant, we have a fuel and oxidizer which is fed to the engine through the injector. We have injector, and from here it's going to mix up in the chamber, and then from the chemical reaction it's going to produce a thrust for the system. Let's see for this. So this is example on liquid propellant system.
That's one small step for man, one giant leap for mankind.
Saturn V sent the first men to the moon, almost half a century ago. Measuring 110 meters high, and weighing 2,840 tons at liftoff, it remains, to date, the largest and most powerful space launch vehicle ever built. Its tremendous power was due, in most part, to the 5 Rocketdyne F1 rocket engines, located on the first propulsion stage. With a massive power output close to 60 gigawatts, they burned more than 2/3 the volume of an Olympic swimming pool of bipropellant mixture of liquid oxygen and RP1 propellant, to accelerate Saturn V from 0 to 9,660 kilometers per hour, in just 2 minutes and a half, to a height of 61 kilometers, with a maximum acceleration of 4 Gs. The huge flow rates of oxidizer and propellant required in each engine were provided by the turbo pump, a device composed of 2 high-pressure pumps and a turbine, interconnected by a same shaft. The turbine converted the thermal energy from the gas generator's hot exhaust into mechanical energy, to rotate the shaft, which in turn drove the pumps. To ensure proper suction at the pump inlets, a dedicated high-pressure helium system was used to pressurize the propellant tank, and high-pressure gaseous oxygen to pressurize the oxidizer tank. In the heat exchanger, the exhaust gases heated the helium coils, and phase changed the oxygen to gaseous in the oxygen coils. The higher pressure helium and gaseous oxygen then flowed on their independent pipelines, to pressurize the tanks. Exiting the pumps, liquid oxygen and RP1 propellant were introduced at high pressure into the liquid oxygen dome, and RP1 manifold. From there they were forced through the injectors, and sprayed at the top of the combustion chamber, below the injector plate, creating an extremely explosive mist. This bipropellant mixture was subsequently burned, producing extremely hot and high-pressure gases, continuously accelerating as they progressed through the converging section of the nozzle, until they reached the throat, where they achieved the speed of sound. Subsequently they entered the divergent section of the nozzle, and because the flow is now supersonic, they accelerated as the area increased. They then entered the thrust chamber extension, an attached component that improved the thrust chamber expansion ratio, and finally were expelled at high speed to the atmosphere, providing thrust. To resist the 3,300 degrees Celsius of the combustion gases, the thrust chamber was regeneratively cooled. The wall was made of hundreds of thin-walled, small-diameter hollow tubes, within which the propellant, prior being injected in the combustion chamber, flowed at high velocity, removing heat by forced convection. The extension's wall was protected differently, by a barrier of cooler gases from the heat exchanger. These gases, at 660 degrees Celsius, were discharged alongside the upper side of the thrust chamber extension inner wall. The impressive F1 rocket engine remains, to date, the most powerful single-chamber liquid-fueled rocket engine ever built, and successfully operated.
And we can have we will know the performance of the rocket based on the specific impulse. So you can see that the difference of the specific impulse give a different performance based on the class of the rocket. So if you see here that the monopropellant as compared to solid is lower specific impulse, meaning that it's a lower performance for the rocket. And we also have a solar thermal rockets and thermoelectric rockets. You can have a look on this, which is solar. We use the concentrated sunlight in order to activate the propellants and also then giving a thrust to this rocket. And thermoelectric, we use a for the thermoelectric, you can we transfer the heat to the propellant by conduction and convections. And this is the example of thermoelectric rocket is resistor jet. And nuclear, as is mentioned here, will use a nuclear reaction for the rocket to be working. So there's a few types of rocket that we have known now. What you can do is maybe you can just Google and have a read on that, get some knowledge from there. There's lots of information out there that you can have a look, but at least now you know a few types of rockets that available and can be used for the propulsion system. So we're going to continue next for this electric propulsion system, and then we can go for the calculations.